Hello everybody, welcome into another lesson. So today we are going to talk about the dot product of two vectors and their applications. Now, this also is probably a little bit of a review for you from earlier in the course. We took the dot product of vectors in 2 dimensions, now we're going to take them in 3 dimensions. So you have some vector u with its respective components in 3 dimensions, and same with a vector v. Well, you may be wondering, why in the heck would you want to take a dot product of 2 vectors? Well, they have a use for determining the angle between 2 vectors, determining if 2 vectors are orthogonal, which is what the term for perpendicular is when referring to vectors. They call them orthogonal instead of perpendicular, but they both mean the same thing. And you can even use dot products to determine collinear points. So let's go ahead and get started with this. First let's talk about what the dot product is. If you have the dot product of vector u and v, all you're going to do is take the first component of each vector, multiply them, plus the second component of each vector, multiply them, plus the third component of each vector, multiply them. And it's important to note that the dot product does not equal the 2 vectors multiplied. The 2 vectors multiplied does exist only in 3 by 3 vectors, and that's going to be the topic of the next lesson, called the cross product. So the cross product is something completely different. When you're taking a dot product, it's going to be a sum, which will end up giving you a scalar or a constant. When we take a cross product, that's going to be another vector, which we'll get into that in the cross product lesson, which is the next lesson. But let's go ahead and do a couple of examples here of the dot product. Alright, so vector u has components 4, 4, and -1. Vector v has components of 2, 5, and -8. So vector u has components of 4, 4, -1. Vector v has components 2, 5, -8. Well, we're just going to start out by taking the dot product. So all I have to do, take the first entry from each of these vectors and the first component, so that would be 4 times 2 plus, I'll take the second components of each vector and multiply them, so that'd be plus 4 times 5 plus that -1 times that -8. So let's simplify a bit. 4 times 2 is 8, plus 4 times 5 is 20, plus -1 times -8, that's plus 8. 8 plus 20 plus 8 gives you 36. So the dot product of vector u and v is going to be 36. Now let's do one more for the dot product, because the dot product itself is pretty simple. Especially if you understand how to do it in the 2 by 2 system. Doing it in the 3 by 3 is really no different. You just have an extra component. That's all it is. Alright. Vector u has components 3, -1, and 6. Vector v has components of 4, -10, and 1. So vector u has components of 3, -1, and 6. Vector v has components of 4, -10, and 1. So let's go ahead and find the dot product. So again, take the first component of each vector, multiply them. So I'll take 3 times 4 plus, I'm going to now take the second component of each vector and multiply them. So that -1 times -10 plus, I'll take the third component of each vector and multiply them, so 6 times 1. I simplify this, I'll get 12 plus 10 plus 6, which would end up giving me 28. So in this case, the dot product of vectors u and v would be 28. Alright, so we have found the dot products. Now let's put this into practical use. And the first stop with this is going to be finding the angle between two vectors. So if you have two vectors and you want to find the angle between them, what you're going to do is set the cosine of theta equal to the dot product of your two vectors divided by the product of the magnitude of your two vectors. Let me grab my phone for the calculator. Okay, so to find the angle between two vectors, it's going to be the cosine of theta equals the dot product of your two vectors divided by the product of the magnitude of your two vectors. And of course, in the end, you would just take an inverse cosine of both sides and you would be able to solve for theta. Today we'll use degrees. I think it's best to use degrees today. So let's do some examples of finding the angle between two vectors. Alright, so I have vector u has components of 0, 2, 2. And then I am given that vector v has components of 8, -4, and -10. Alright, so vector v has components of 0, 2, 2. Vector v has components of 8, -4, -10. Well, let's use that formula for the cosine of theta equals my dot product of vector u and v divided by the magnitude of vector u times the magnitude of vector v. Well, it would probably help if I go ahead and work this out on the side. Let's take the dot product of vector u and v. Let's start there. So the dot product of vector u and v, I'll take 0 times 8, plus I'll take 2 times -4, plus then I'll take 2 times -10. So to simplify this, I would end up getting 0 minus 8 minus 20, which would give me -28. So I at least now have that dot product component of -28 for the numerator. Now, of course, I should probably find the magnitude of each vector. So the magnitude of vector u, that's going to equal then the square root of my 0 squared plus 2 squared plus 2 squared. Well, 0 squared is just 0, so this would turn into the square root of 4 plus 4, which would equal the square root of 8. And I'm actually going to leave it as the square root of 8 temporarily. There's a reason for that. Now let's find the magnitude of vector v. So that's going to equal my square root of 8 squared plus -4 squared plus -10 squared, which would turn into the square root of 64 plus 16 plus 100, which would turn into the square root of 180. And actually, I think what we're going to do with this square root of 8. Let's simplify that into 2 times the square root of 2. I probably should have done that to start, but the square root of 180, I know that would be the same thing as the square root of 36 times 5. So that would be 6 times the square root of 5. So that magnitude of vector v is 6 times the square root of 5. Let's see if we can simplify this a little bit here before we go to take our result. So this would turn into negative 28 over 12 times the square root of 10. Well, we know we can divide both numerator and denominator by 4, which would turn into negative 7 over 3 times the square root of 10. So you'll get the cosine of theta equals negative 7 over 3 times the square root of 10. So that means that theta itself is going to equal the inverse cosine of that negative 7 over 3 times the square root of 10. Okay, well, the inverse cosine is defined between, or actually including 0 to 180. That's where it's defined. This is definitely going to be a second quadrant angle because that's a negative value inside of the cosine. So let's go ahead and start figuring all this out. So if I take, let's see here, 3 times the square root of 10, then I'll take negative 7 and divide by that answer. Then I'm going to take the inverse cosine of this answer. If I round to the nearest degree, I get approximately 138 degrees. So we'll just round to the nearest degree today. There is approximately an angle of 138 degrees between vectors u and v when you do the inverse cosine. Let's do another for finding the angle between two vectors. I'll leave this formula up, but of course the vector values themselves are going to change. I'll even leave the dot product format up and the magnitude of each vector format up. Sometimes it just helps to do this work off to the side. Alright. So vector u has components of negative 1, 3, negative 1. Vector v has components of 2, negative 1, and I think positive 5? Yes. 2, negative 1, positive 5. So vector u has components negative 1, 3, negative 1. Vector u has components of 2, negative 1, 5. So we have to find the angle between the two vectors. The cosine of theta equals the dot product of these two vectors divided by the product of the magnitude of these two vectors. So let's start by finding the magnitude of vector u times v. So that's going to be, I take that negative 1 times 2, not plus 2, what am I saying? Negative 1 times 2 plus that 3 times negative 1 plus that negative 1 times 5, which would simplify into negative 2 minus 3 minus 5, which would be negative 10. So I get a dot product of negative 10. I'll just go ahead and plug that in up here. Now I should go ahead and find the magnitude of each of these vectors. So the magnitude of u, that's going to be the square root of that negative 1 squared plus 3 squared plus the other negative 1 squared, which would simplify into the square root of 1 plus 9 plus 1, or simply the square root of 11. So now we know the magnitude of u is the square root of 11. We'll go ahead and plug that in. Now let's figure out the magnitude of v. So this would be the square root of that 2 squared plus that negative 1 squared plus 5 squared. So this would simplify into the square root of 4 plus 1 plus 25, which would end up becoming the square root of 30. And we really can't simplify that any further. And I think we can leave it like that. It's going to be rather hideous, but, well, this would really turn into negative 10 over the square root of 330. And we can leave that be. Now, that means that theta itself is going to have to equal the cosine inverse of that negative 10 over the square root of 330. So now we'll just do the inverse cosine and we'll get an approximation to the nearest degree. Alright, so let's see, the square root of 330. Now let's take negative 10 and divide by that answer. Now take the inverse cosine of that. You get approximately 123 degrees. So that gives you an angle between these two vectors of approximately 123 degrees. Alright, so we have talked about the angle between vectors as an application of the dot product. Now, the next thing we're going to do is determine if two vectors are parallel, orthogonal, or neither. So, how do we determine that? Well, parallel vectors, if two vectors are parallel, you don't even need a dot product. All you need to show is that one vector is equal to the scalar multiple of the other. So all you have to do is show that one vector equals the scalar multiple of the other vector. That's all you need to show that they're parallel. Now, for orthogonal vectors, if you want to talk about orthogonal vectors, again, that's the vector term for perpendicular vectors, forming a 90-degree angle between them. If the dot product of two vectors is equal to 0, then the two vectors are orthogonal. Which, let's think about that a second. Let's go back to the formula for the angle between two vectors, right? The angle between two vectors, okay, so that's going to be the dot product of u and v divided by the magnitude of vector u times the magnitude of vector v. Okay, well, if the dot product is 0, it doesn't matter what your magnitudes are. You'll get the cosine of theta equals 0. Well, what angle gives you a cosine of 0? That'd be 90 degrees. So they're orthogonal. So the dot product of two vectors when they equal 0 means that the two vectors are orthogonal to each other. And then obviously, if neither of these two criteria apply, then we can say that they're neither. They just plain intersect. Alright. So, let's do some examples here. We have vector u is equal to components negative 12, 6, 15. Alright, now vector v is equal to components 8, negative 4, negative 10. So we have a vector u with components negative 12, 6, 15. Vector v is 8, negative 4, negative 10. Are these two vectors parallel, orthogonal, or neither? I actually like to start out by trying to show they're parallel first. Basically, don't try to take the dot product unless you need to. That's your last resort. Try to show if they're parallel first. So we know what vector u equals. Let me restate what it is here. Vector u has components of negative 12, 6, and 15. Can we factor out any common factors on vector u? We can factor out a common 3, can't we? This would be the same thing as 3 times the vector negative 4, 2, 5, right? So we have 3 times negative 4, 2, 5. Start out by factoring what you can factor. Now, what about vector v? So let's restate vector v right here. That's 8, negative 4, negative 10. Well, can we factor out any common factor from vector v? We could certainly factor out a 2. That would be 2 times, then you would end up getting 4, negative 2, negative 5. Well, would you look at that? It looks a lot like between vectors u and v, you have a multiple of negative 1. So in fact, we can factor out a negative 1. You'll end up getting negative 2 times the vector 4, negative 2, negative 5. Now, to obtain your scalar multiple, then, what you want to do then is just set one vector equal to the other. Just take your coefficient. If u equals 3, because these two vectors are otherwise equal, right? I don't know why I factored out a negative. I probably shouldn't have done that. Left the other negatives in. There we go. If u has a scalar of 3, if v has a scalar of negative 2, well, that just means that u is going to equal negative 2/3 of v, right? Because otherwise your vectors are equal. Now you just take your scalar multiples, take one vector's scalar multiple, divide it by the others, you can get that u equals negative 2/3 times v, or you could also say that v equals negative 3/2 times u. You can go either way. But we have proven that these two vectors are scalar multiples of each other. Therefore, we can say that vector u is parallel to vector v. So, since these two vectors are scalar multiples of each other, they are therefore parallel. Alright. Let's do another one. So let's see here. Vector u has components negative 1, 3, negative 1. vector v has components 2, negative 1, 5. So vector u has components negative 1, 3, negative 1. Vector u has components of 2, negative 1, 5. I think it's very plain to see these are not scalar multiples of each other. So they're definitely not parallel, right? They don't even have a chance to be parallel because they're not scalar multiples of each other. But are they orthogonal then? That's the next question. In order to determine that, we need to take the dot product. And if the dot product ends up being 0, then they are orthogonal. So we'll take that negative 1 times 2, plus we'll take that 3 times negative 1, plus we'll take that negative 1 times 5. So that's going to give you negative 2 minus 3 minus 5. That just gives you negative 10. Well, you need a dot product of 0 for them to be orthogonal, so these two vectors are neither parallel nor orthogonal in this case. They're neither. They just plain intersect. Let's see the next one here. Let's see, 3/4, negative 1/2, two, four, 10, and 1. So we have two vectors here. Vector u is 3/4, negative 1/2, and 2. Vector v is 4, 10, and 1. If we really take a look at this here, sure, we could multiply vector u by 4, and you would end up getting 3, negative 2, and 8. But either way, these would not be scalar multiples of each other, so they're definitely not parallel. Now, what about the dot product? Can we try to determine if they are orthogonal? So let's take the dot product. So we'll take that 3/4 times 4, plus we'll take that negative 1/2 times 10, plus that 2 times 1. So 3/4 times 4 is just 3. And then negative 1/2 times 10, that's minus 5. And then 2 times 1, that's plus 2. Alright, 3 minus 5 is negative 2, plus 2 is 0. What do you know? The dot product is 0, so these two vectors are orthogonal. So you could say that vector u is orthogonal to vector v. They are in fact orthogonal because you got a 0 dot product. Alright, so we got one last topic here. One last topic, and that's going to be about collinear points. So we want to talk about some collinear points. So you can use vectors to determine if 3 points are collinear. So let's say you have some points P, Q, and R that are on a line. That's what we're going to call them. You have some points P, Q, and R that are on a line. Well, this goes to the idea that they are collinear, which is a term we haven't used much since geometry, meaning they're on the same line, if vector PQ is parallel to vector PR. That's how you would determine that. The 3 points are collinear if vector PQ is parallel to vector PR, which would have to mean that these two vectors are scalar multiples of each other. So let's go ahead and try to determine a few of these, see if we got collinear points. So point P is at the point 5, 4, 1. This is just an ordered triple, not a vector. Point Q is at 7, 3, -1. And then we also have a point R, which is at 4, 5, 3. Okay, so we have points P, Q, and R. The idea is to determine if they are collinear or not. So we need to, of course, determine, is vector PQ parallel to vector PR? In other words, is one vector a scalar multiple of the other? And if they are, they're parallel. If not, they're not. So first thing, find your vector PQ. So let's find vector PQ. Well, that would end up being 7 minus 5, which would be 2. And then you'll have 3 minus 4, which is -1. Then you'd have -1 minus 1, which is -2. Now let's find vector PR. So vector PR, let's take 4 minus 5. That would end up being -1. 5 minus 4 is going to be +1. And then 3 minus 1 is going to be 2. Well, let's really look at this here. It looks like the first couple components of vector PR involve some form of 1. Let's say I took half of vector PQ, I would end up getting 1, -1/2, -1. These are not scalar multiples, are they? So that means these two vectors they're not parallel, which means they are not collinear. They do not lie on the same line. Simply for the fact that they are not parallel vectors, they are not collinear. I got more of this. Let's see what we got for our next points. Alright, -2, 7, 4 for point P. -4, 8, 1 for point Q. And then 0, 6, 7 for point R. So we have 3 points, P at -2, 7, 4, Q at -4, 8, 1, and R at 0, 6, 7. First thing we want to do is set up vector PQ. So that's going to be the -4 minus -2, so -4 plus 2 is -2. 8 minus 7 is 1, and then 1 minus 4 is -3. So vector PQ has components of -2, 1, and -3. Now, vector PR So we'll end up taking 0 minus -2, which actually is going to turn into 0 plus 2, which is 2. And then we'll take 6 minus 7, which is -1. And then 7 minus 4 is 3. Well, let's take a look at this here. It looks very much like they're scalar multiples, right? In fact, they are, because you can factor out a common -1 on PR, and you could get negative of the vector -2, 1, and -3. So what do you know? Vectors PQ and PR are scalar multiples of each other, because vector PQ would equal negative of vector PR, or you could say that PR is the negative of PQ. You can go either way. Either way, they are scalar multiples of each other. You have two vectors going in opposite directions, but they're still parallel. Even if they're on the same line, they can still be parallel. Vectors work differently than lines in that sense. They could be attached to the same line, but if they're constant multiples of each other, they're considered parallel vectors. So even if, in fact, you would have gotten no scalar multiple per se, just would have been +1, they would still count as parallel vectors, which would have given you collinear points. But since we can clearly see a scalar multiple, we can say that all three of these points are in fact collinear points, due to the fact that these two vectors are scalar multiples of each other and parallel. Alright, so that's it for this lesson. Next lesson we're going to get into the cross product of a vector. So I hope everybody has a great day. Take care.